Okay, so on the previous questions that you have is something like this, right? You have C2H5OH, which is the chemical structure for ethanol, plus 3 oxygen turns into CO2 and 3 water. And the delta H reaction that I'm written here is negative 1,368 kilojoules per mole of ethanol. So calculate the amount of energy released in terms of heat when 30 grams of CO2 is produced. So as always, like any chemical reaction, just get your instinct to convert everything to moles, whether it's given in concentration, mass, density, whatever, convert it to moles. So we have 30 grams of carbon dioxide, and you look at the periodic table, the molecular weight is 44 grams per mole. So the number of moles of CO2 is just the mass divided by the molecular weight. You get 0.6818 moles CO2. My suggestion, don't round the numbers until the very end. If you kind of tired of writing down 7 digits, keep everything around 5 so you don't have any rounding issues. Use it as a good idea to just not round till the end. Keep everything to about 4 or 5 at least. Okay, so this is what we're going to do. Number of moles times delta H reaction times the mole ratio. So in this case, I'm producing 0.6818 moles of CO2 times the delta H of reaction. But notice that it's written in terms of moles of ethanol, which is my C2H something. So we kind of have to put in, similarly to our balancing chemical reaction, finding theoretical yield, I'm trying to cancel out the unit of mole of ethanol and moles of CO2. So I'm going to look at the balanced reaction. I have 1 to 2 ratio. So I'm going to multiply it by 1 moles of ethanol for every 2 moles of CO2. So it's the same thing. You start with moles of CO2, you're going to divide it by the moles of CO2. So this cancels out, the mole cancels out, ethanol cancels out, and what we're left with is just a unit of kilojoules. And just multiply everything together. This comes out as negative 466.36 kilojoules. Now, where is the mole ratio becomes a thing of interest? I gave a couple of, or at least one of you, an example that looks like this. So suppose that 2A plus 3C turns into 5D. And suppose that I know the delta H of reaction is going to be negative 1,000 kilojoules per mole of A, right? But this is now written per moles of A. So that's kind of becomes where things becomes a bit more, where the formalism becomes useful. So suppose that I produce 1.8 moles of D. What is the amount of heat that is being released in this particular reaction? Okay, Q is the number of moles times the delta H of reaction times the ratio. I always put the ratio in there just to get that in the back of your mind. So I know the number of moles is 1.8 moles of D. The delta H reaction, however, is written as 1,000 kilojoules, negative 1,000, for every moles of A. So we kind of have to do a unit conversion using the stoichiometry. So I'm trying to cancel the moles of A and cancel the moles of D. So I have 2 moles of A, so 2A for every 5D. So that's what I'm going to put it in the bottom. It's a bit of a formalism because it's basically unit conversion. So hopefully you can see that the mole cancels out. Use a different color. A cancels out. And the last one, D, also cancels out. There. So in the end, the unit that we're left with is just kilojoules. So this becomes whatever the number is. It's actually, it's for my other class, but that's fine. 1.8 times negative 1,000 times 2 to the 5, and the unit that we have in the end is in terms of kilojoules. Okay. I'm not going to calculate the whole thing. Okay. Yeah.
Does it work if we put 3C in the numerator?
Oh, because the delta H of reaction is written for every moles of A. Yeah. So it's just something to be watch out for. But so most of the time you don't have to worry about it. It's just most of the time you don't have to worry about it. Okay. So before we go into kind of doing the calculation here, I just want to explain how enthalpy of reaction is measured. This is a thing called the Bohm calorimeter. The setup pretty much looks like this. So you put your sample inside of this, and then you put everything into basically a really rigid metal container, that one, and you seal it really tight. And because you've already sealed the materials and put a bunch of oxygen gas in it, for example, it's really hard to stick a match to light up your product, your reaction. So instead, you have a couple of wire that kind of goes into the material. So you have a couple of wire, and essentially you just go give it a little bit of a spark, similar to what you have in your car. The spark plug pretty much operates the same way. You give it a spark, and then the reaction happens. When the reaction happens, this thing becomes really hot, and you have hot object, and then it's going to transfer the heat that is being produced to the surrounding water. Now, to the surrounding calorimeter, I should say. Now, the calorimeter is mostly made out of water, so you have a large body of water. But you also want to know the temperature of the chemical reaction that is being produced, so you have a thermometer there. And then you also want to make sure that the heat is being spread out evenly throughout the entire calorimeter. So you have a stir, motorized stir of some sort to spin the water around so the temperature is equilibrating. And you will then find out the amount of energy released from a particular chemical reaction by looking at the change in temperature. And if you know the heat capacity of the entire calorimeter, then you can back calculate the amount of energy produced from the reaction. Now there's a few things about calorimeter. That is, there's a lot of components in it. You have water, you have a stir, you have the container, you have the thermometer, you have the wire. So what happens is that it's really not convenient to write down everything for every single mass of the stir bar, the container, the water, and so on. So instead, you're collapsing everything to just a unit of Cp without any mass in it. And remember, the heat capacity unit means the energy needed to increase the temperature of some object, really, some stuff, by 1 degree Kelvin. So essentially, we collect this stuff to be the entire thing. So we don't have to worry about the mass. Hence, you'll find the unit of a Bohm calorimeter, or a calorimeter in general, to be in terms of just joules per Kelvin or joules per degree Celsius. Anybody know why it's called a Bohm calorimeter? No? Where do you guys plan to take your labs for lab equivalent for this class? SMC? I don't think they do actual Bohm calorimeter at SMC. But well, it's called a Bohm because whenever you burn organic material, it produces a lot of gas. So what happens is that if you're not careful and the container that you have your reaction can't withstand the pressure that's built up, it will actually turn into an actual bomb. So hence the name Bohm calorimeter. In fact, pretty much a bomb is that. It's just a really exothermic chemical reaction that produces lots and lots of gas molecules really quickly so that everything just, the volume increases and it just splatters everywhere. So partly the name bomb is just to, tell you to be careful with it. Because if you're not careful, it becomes an actual bomb. I think if you live closer to the valley and I guess you won't be taking, if you live closer to the valley, I think some of the community colleges that does the lab for UC Extension uses an actual Bohm calorimeter, which is kind of fun. But I think if you're going to SMC, you guys are using the cup calorimeter, if any, right? Which is the same thing, same principle. Anyway, so that's just how the bomb calorimeter work. You put your material, you burn it, and make sure that it's in a nicely sealed container that's quite rigid so it doesn't explode. And you just measure the amount of heat released. So this problem is really the same thing as large body of water. You have a hot object and you have a cold object, and you're finding out what is the amount of energy released. But instead of finding out T final, you're really trying to figure out the amount of Q. So the setup of the problem is the same. But let me just kind of read out the questions. You already have it in you, with you. The thing that we burn is 1.685 grams of benzoic acid, and I know that the delta H of reaction is this much, and I also know that the change in temperature to be 2.821 degrees Celsius. So it's really the same problems of heat exchange. You have hot object exchanging heat with the cold one. So what we have is that Q of the reaction plus Q of the calorimeter, and the sum of which equals to 0. This is what we're trying to find out, so I'm going to collect it. Q of reaction is the negative Q of the calorimeter. And usually we put this as mass times Cp, excuse me, times delta T. But again, for the calorimeter, because there's so many different components in it, we just collapse the mass and the Cp together. So we call it just the Cp of the calorimeter times delta T. Right? So let's just kind of put in some of the information that we have. So this is negative Cp of times delta T. And before I go to there, I'll just put in the Q of the reaction is equal to the number of moles. Actually, what are you trying to solve? Actually, we're trying to solve for Cp, not trying to solve for Q of reaction. So the number of moles times the delta H of reaction times the ratio. But in this case, I don't care too much about the ratio. And plus that equals to 0. Sorry about that. We're not trying to solve for Q. I know the number of moles is just 1.685 grams divided by, if you look at the molecular structure of benzoic acid, so you have 7 carbons, 6 hydrogens, 2 oxygens, and so on, you'll find that the molecular weight comes out to 122 grams per mole times the delta H of reactions. In this case, is negative 1,385, I think. Let me just double check. Oh, 3,228. 3228. Kilojoules per mole. Is actually per mole of benzoic acid, but what we have here is also moles of benzoic acid. This is per mole of BZ, so the unit cancels out, hence I don't worry too much about the unit. Plus Cp, which is given to us as, actually that's what we're trying to find out, Cp times delta T, and the delta T is 2.8121 degrees Celsius. Okay. And the sum of which is going to be equal to 0.
Sorry, for the first part, why does it not matter that we don't have
the ratio? Because this is written in terms of moles of benzoic acid, and the delta H is written per moles of benzoic acid. So the unit already cancels out. We're calculating the moles of benzoic acid, and this is 3228 kilojoules per mole of benzoic acid. So it nicely cancels out already. Yeah. I'm skipping a few steps, that's all. So let's just kind of rearrange this whole thing. Cp is going to be equals to 1.685 divided by 122 times negative, negative of that. So you have a double negative there. Excuse me, I forgot to mention that. So you have a double negative, and then this is divided by 2.821. and the unit's going to be kilojoules per degree Celsius. Just watch out the double negative, and if you find that your heat capacity is negative, that means you have a negative error somewhere, because the amount of energy needed to increase the temperature of an object shouldn't be a negative value. So it's kind of a useful thing to kind of keep track of when you're doing a calculation. It's like, oh, it's not supposed to be negative, then there's a calculation error somewhere. The same thing with the heat exchange problem that you've done so far, that if you know that the temperature of your solution is supposed to go up instead of down, and you find that the temperature goes down, there's a calculation error somewhere. So in this case, the heat capacity of this particular object is 15.8 kilojoules per degree Celsius. So far, so good? Yeah.
Can you explain again how you chose what values of kilograms, what definitions of kilograms, and how you can make the assumption that the mass is just part of the CP? Because if the problem's just like dropping metal into a hot water, why
Yeah.
do you do that?
It's kind of the same thing, isn't it? The only changes that we did is just that. This is still the same thing. It's just in terms of the heat capacity, it's the reason why we forego the mass is that there's so many components associated with it. It's not useful to put everything, the mass of everything. So really the heat capacity comes from the mass of your thermometer plus the mass and the heat capacity of your stir plus the mass and the heat capacity of your water. So instead of you putting everything as single in one large thing, you put it as a CP, right? To make it a bit easier to calculate. Sorry? Yeah. Well, you're incorporating the mass into the whole thing, essentially. So why don't we do one more question? Oh, yeah. Mm-hmm. Yeah, yeah. It's released per 1 moles of benzoic acid. So let's do another example. Instead of looking for the CP, I want you to try to calculate the amount of energy released from the chemical reaction. And let's make this a bit harder. Instead of 2 objects exchanging heat, let's do this with a coffee cup calorimeter, which is probably what you're going to do later on. So suppose that I have a coffee cup calorimeter, and inside this coffee cup, I have 200 grams of water. So I know this is my cup. This is my cup. And I know that the heat capacity of the cup is going to be, it's not on there, is going to be 100 joules per degree Celsius. So that's the heat capacity of the cup. Inside this cup, I also have 200 grams of water. I know that the heat capacity, I know the mass is 200 grams, and the heat capacity of the water is going to be 4.184 joules per grams degree Celsius. And then inside of this, I have a chemical reactions, and where trying to figure out something. It's okay. Oh, let's just make it simpler because I can't think of anything too complicated right now. 0.3 moles of A reacted. You don't need to know the information, so your goal in here is you're trying to find out the delta H of reaction per mole of A. So this is your goal. The information that you have is that when you put in the thermometer, you find that the initial temperature is 23 degrees Celsius. And after the reaction happens, it releases energy to the cup and the water. So heat is released to the cup and the water. You find that the final temperature goes up to 25 degrees Celsius. So what is the delta H reaction per moles of A? And the unit of this answer is supposed to be in the end, say joules per mole of A. So that's the unit of the delta H reaction that I want you to calculate in the end. And we'll give this, I don't know, 10 minutes.